Мама, я тебе тетрадки принесла. Мама, я тебе тетрадки принесла.
Спасибо.
А вот в этой 3 страницы тебе давать?
Молчи, пожалуйста.
Надо на балкон,
So I propose that we shall start. If somebody join us, then it's okay. We can do it in the process. So do you hear me, dear friends?
Yes, we do.
Very good. So the first exercise we shall take the aim of this exercise is to understand that 2 notes which are different, like granny and square, so they are in some sense completely different. That we noticed that the note group of the right-handed and left-handed trefoils are the same, but they are in this position that one is the mirror image of the other. So now we construct 2 notes. Actually, they are absolutely different. No one is the mirror image of the other one. And so this is the classical example of knots, maybe the first one from the point of view of number of crossings that knots are different, and however they have the same group and the same presentation. So of course I understand it is difficult to explain, so maybe we discuss, I look at my own and we compare explanations that in this picture and explanation that I made. So sorry, just a moment. So yeah, I do. So maybe I don't know whether it make a little bit bigger. I don't know how. Yeah. Okay. So you see, Rafael, do you see your proper?
Yes.
Okay,
Yes,
very
I
good.
do. But by the way,
So,
I have a question about it to maybe avoid all the computation, because it's a bit.
yes, it's a good idea, but you can just explain, and we compare with yours and my own calculations. So can you? So finally, we should have these two.
I got it, but with different letters. But I don't think it matters, the letters. I got it with T, X, and W or Y, I think. Or T, Y, and W.
Yes, but
it just depends. It
yeah,
just
but
depends
anyway.
on the knot.
Anyway, what? Tell me, and I look at my own. For example, this one is simpler, right?
The left one is the simplest.
And so your
there is a page after, yes.
So we get
yeah.
I have another one. Just to make, for me, I let this guy and these two. They survive. They persist to the end. This, in what is in your notation, is Y, and this is what is in your notation W, and this is notation is S, right? S, I see. Okay. So as for me, I let these three, and then because of other points, I expressed the other arcs with the help of Y and W, with the help of Y and S, and then these guys give us finally relation. Y relation, maybe this one. I escaped. So and then finally I got this beautiful stuff. And another one is a little bit more complicated.
It's a bit more tricky, yeah.
I'll tell you what yeah, but in the previous one, it is no matter. I also made, but they are, you see, they are absolutely symmetric. So
No,
I
all is
left,
symmetric. There is no problem.
this one.
It's just not making computation error, especially at the end, because it gets pretty big.
Yes. So as for me, I made this one, and then again this one, and this one. This is the same as in the previous case. Y and W, it's okay, but this a little bit, you're right. This makes a little bit tricky, and finally I got the two presentations with Y, W, and S, and you are getting
I just take
Y.
the letter. Y,
Sorry?
TYT and YZY. I just, because I substitute other letters, it was just easier somehow for me to compute. If we can
So
say it
sorry,
easier,
I see it's too small. Maybe I may make it bigger. So, excuse me.
There is a magnifier on the bottom.
Yeah. So this is Z, and this is, what is your notation for this one?
So you see on the graph on the top, there is big 1, big 2, big 3, and so on and so on. And
yes,
the equation, so the first equation is the intersection big 1, the second one is intersection big 2, and so on. So I substitute the fourth one. So I substitute this one, then I substitute the last one, and then I substitute the second one.
Yes, I can also tell you that, sorry for that, that as for me, and I think this is not only me, but more or less other people are using, they even not introduce another notations for other arcs. They simply they have this one, and they simply, because of Wirtinger, they make notation as the corresponding conjugations of YS or YW, and so, and then you make equations of them, and it will be okay.
Okay.
Right. So, Natalia, do you have comments?
Oh,
Somebody else may have comments to this stuff. No comments, then so let us look. So let us start the exercise 2. Why I made this exercise 2? Because we'll consider braid groups today, and this is why this notation B, because of notations for braids, B, English word braid. So, and because this is only 3 strands, there are no commutations, all of them are, there are only 3 strands, they're close, and there is only one relation. Only one relation. It should be relation, if there are maybe sigma 3, then sigma 1 and sigma 3, they shall commute. But as we have only sigma 1, sigma 2, this is also, I use this more or less standard notations for braids. So there is only one relation, the Reidemeister 3 relation. Okay, but you know that we met this group in the previous context. So this is the group of trefoil. This is a group of trefoil. And same relation that we already obtained in our context. So this is the aim of this exercise is to put braid group on 3 strands in the context of matrices, the object that you know very well. So let us consider the matrices with entries in numbers, integer numbers, and with the determinant equal to 1. So the same way as you're considering matrices of rational numbers, of real numbers, or complex numbers, the matrix is invertible if its determinant is invertible. So 1 is a very beautiful invertible element in Z. So we have this is a group. So for each matrix we can find its verse, and of course you have unit matrix. Very good. So, and let us consider 2 following matrices. Of course, you see that they have determinant 1. And the first thing is to consider the following, that there is a homomorphism, from B3, from braid group to SL to Z, and we define it on its generators. Sigma 1 goes to this matrix, sigma 2 goes to this matrix, and it is first of all, it is necessary to understand that this is a homomorphism. This is a well-defined homomorphisms. I try to look at the exercise made. So as we are doing algebra now, we can remind the presentation, and the first I look at the I look more like this. It's okay. So it's that matrices generate this group. It's a bit complicated. I didn't give this as an exercise, so Rafael?
Yes.
This your remark? It's quite complicated.
Yeah, it's not trivial.
Yes, so it's not complicated that you don't need any solid group theory, but you need to case by case to see how they generate,
Yeah.
present every matrix and so on. So I didn't give this because of quite a lot of labor. I didn't give this exercise as an exercise. But if you notice, it's very good that actually we see that this becomes an epimorphism. So, but I would like only just to mention, not to make you work too hard for this. So, okay. So we just leave it as a remark, which is true, but we don't prove it. Okay. So, but I don't see that we need to prove this. So actually, this is what we need to prove. That the image equal to this one, this equal to this. We need to consider this and this. So it means that formally we need to do, just look, we need to do the following, that A, B, this is A, this is D, this is again A, equal to B, A, D. So this is a concrete work in these matrices. So you need to prove this. You need to verify this. This is not. Yes, this is the first year linear algebra work, and actually it is usually in your exercises for linear algebra, you have actually the matrices with the integer coefficient. You don't have usually the matrices with coefficients in P, and so on. So it's quite standard work, the multiplication of this matrix, and you need to verify this. This is concrete work. Do this, right?
Yeah, no, I did. I mean, didn't type it because it's quite long to type. But
yes, but I'm sure that you can, and but just to be formal, that if your group is given by generators and relations, by presentation, you need to justify that you have a homomorphism. You need to see that the image relation is satisfied, right? So this exists. Then the second stuff, what does it mean? We have some group theory. I remind, of course, I'm sure you know what this element is central. Central means it commutes with everybody. So, right. So this is how to verify that yes, but actually you can do this simpler, I think, because it's not necessary for the proof, but if you know that A and B, they generate this group, you need to know that center element commute with A and commute with D. So you don't need to
No, I
with
took
this.
I took A, which is given. I just didn't write all the multiplication, but A is 1, 1,
So
0,
yes,
1.
so
Yeah,
so
it's what I did.
then you did what is necessary, right?
Yeah,
Exactly.
yeah.
I see now that this is the correct computation. Yes. So finally A and D, and when we calculate the A equal to D, so this is 0. Our determinant is equal to A squared or D squared, and then we have only two possibilities, right? Very good. This is what we see, and now we can I didn't wrote, sorry, the modular group or projective. This is when you factorize by the center, so, right? And this is the crucial thing, that this element is central in the braid group. This element is central in the braid group. So and then we can also map it to the center as if it is central. So where is your, yes, this is a good example how you are working with the braid relations. So you write there, and yes, and the same you can do with the second generator, and it's okay. And you see here that you are using that it is in the square. It's not enough. So very good. Then what was the next? Yes, so we construct this one, and yes, this is a good thing. And sorry, I made the but if you see that these guys are braids, there is a beautiful, because this fact is that this is in the braid group, and braid group we shall consider what it means geometrically. So there is a geometrical proof why this element is central. The proof is the following, that look at the braid of 3 strands. You have a frame, This is the trivial braid on 3 strands. Now it may be difficult, maybe not, just boring to consider this, to write down, maybe not boring. So, okay, let us try to do this. Okay. This is sigma 1. This is sigma 2. And this is again sigma 1, right? So what do you see? This is this object without square. So can you see what happens geometrically, how to construct this object from this one geometrically?
I didn't really understand, to be honest.
So do you see this braid?
Yeah.
This is a braid, right?
Yes, yes.
And this is exactly this braid without square. Sigma 1, sigma 2, sigma 1, right? This is, if you again put here the same braid, you will get sigma 1, sigma 2, sigma 1 squared. But this braid can be constructed geometrically. How can you construct it geometrically, this braid?
Can you explain again the draw of sigma 1, sigma 2, sigma 1?
Sorry?
I don't get it. The
This is...
draw on the right. Yeah, how do you get it?
Okay, very good. Very good. Sigma 1.
Okay.
Sigma 2. Right? Sigma 1 again. You see?
Yeah, yes, I see.
So you see that this one is in his place. This strand, actually, this is vertical, right? The first one goes to the third place. The third goes to the first one. So how can you obtain this geometrically? This is the rotation of this frame by 180 degrees. You see? If you rotate this frame, you just consider this like a frame. Here, this is made from wood, and here are 3 strands. Okay? And now let this one be fixed, and this one should be rotate by 180 degrees. Then the first one will go to the third one, go to the first. The first go to the third. And this one is constant, like here, right? Natalia, do you agree with me?
Yeah, it's clear. It's clear.
Yes. So actually, this one now with square means that you made a rotation. Made rotation of your frame by
360 degrees.
yes, 2p. Sorry, my p is terrible, but anyway. And so, from geometrical point of view, if you now see rotation by p, you, for example, take here a knot, and then if it is rotation by 2p, then you not a braid, sorry. You can simply move this braid by this rotated by 2p strands. And without any problem, you can have your braid here. You get through this twist without any change. Your braid from upper position will go to the, from lower position will go to the upper position. This is geometrical proof that this is a central element. Because this is nothing but a full twist. This is 180 degrees, this is half twist. And sigma 1, sigma 2, sigma 1 squares is full twist. So you can simply move with the help of your full twist, you can simply move your braid from here to here. So maybe it's from the first time it's not absolutely clear, but if you can look, you can make these strands by yourself. You see that this braid moves. It's simply the same. The braid simply makes its rotation by 2p. The braid, which is in the upper position or in the upper position, made its rotation when it's going down 2p. Okay. Very good, but this is just explanation. If you have some problem, this is nothing. This is only explanation. Formal proofs are given here. So now as this element is central, this element is central. Now we can okay, this will be later, but anyway, about this is quite complicated. I think so that this group has this presentation as Z over 3Z, free product with Z to Z. Natalia, do you see that this exercise is, I considered it, I made it, especially because of your question last time? You remember? When we were considering the presentation of knots in the presentation of torus knots, then you suppose that maybe there will be just a free product of the two groups. No, there it's not a free product, but
yes.
If you need to factorize, by this, then you have. So this fourth exercise is especially for you, or answer your question. But after factorization, you are right. You have this thing. But in general, we can say that in the knot group, there are no elements of finite order. So we get this element, for example, if you take unit here, you have Z over 3Z. There are a group of 3 elements, and here a group of 2 elements, if you have here. But then we get here. So let us look at our stuff. Let us look. So yes, so you are right. So yes, you're right that we have trefoil, and here you have like this. And when we factorize by the center, we get yeah. So you see that here center you need because it is you need to commute with Y and Z, and it happens. The explanation is the following: that it happens when you have the square of Y or the third or the third degree of x. Otherwise, you'll not have the commutation. So, combination. Very good. Very good. So now let us consider, yes, that the same way, if we have Z3 and Z2, we can construct the homomorphism, and if we take into account the remark that Raphael made from the very beginning, actually it becomes a surjective map. So, and the difficult is the sixth one. The difficult is the sixth one. So, do you have some ideas, Raphael, how to?
Well, there is some remarks that can be done. First of all,
No.
PSL doesn't have a center neither, and H, sorry.
Mm-hmm. You mean I'm not sure that this argument is absolutely correct. What is a proof of, from my point of view, is that is the following. It's a little bit boring, but the same way we were considering the free group. When we were considering the free group, we made the solution of the word problem, and solution of the word problem for the free group was the following, that we made in the canonical form. We made in the canonical form each element of the free group. Here we can make, in what is called the syllable form. So if you have, say, you have generator A, or maybe, sorry for that, you are using, Raphael, you are using your following. I just look at your stuff, sorry. Okay. And we'll keep your notations. So you are using Y or A and B, what is your notations for generators here?
In the second part, no, in the second part, I was just a way to show that, for example, F bar exists is equivalent to show that two elements which are in the same class implies that the projection, that the morphism is the same. If A and B are the same class, then F of A equals F of B, without especially taking generator.
No, I don't. Maybe it's not sufficient. So, as for me, so your generator here is A, right?
We can take, yeah, we can.
B, right?
Okay.
F and B. And so there is B minus 1, right?
Mm-hmm.
Here only A. And then there is the analog for the canonical form of this one. So if you have this is cyclic group and this is cyclic group, so you should have the form A, B, say epsilon 1, A, B, epsilon 2, A, and so on. And so on. So you should consider, so the canonical form for example, for solution for the word problem for this group is the following: that if in the free group you were making solution by letters, now you are making solutions by syllables, and you should consider all the cases when it starts with A, finishes with A, starts with B, finishes with A, and so on. So there are several cases, and you consider all these cases, and then you consider all the images of them here, and you prove by considering all the cases that this is an injection. So it's a little bit boring, but I think it's necessary to do. It is not sufficient to make some general considerations. Okay.
Okay. Okay.
So essential is that the syllable solution for the word problem for the, how it is called, for the free product of cyclic group, right? Okay. So, and then now we have our stuff for Hobbs link, for 5.2, for this is Cinquefoil, we understood this is file 1 for Whitehead, for Borromean. So what do we have? So is it in your sheet or in your, no, it is in your subsequent things, right? Right. So this is 5-2.
Yes.
With no, sorry. So there is a little bit sound. Can somebody switch off the sound? Okay, so what do we have? This is the let's see, sorry. Okay. Sorry for that. What are you doing? Can you explain?
Yes, sure. Can you zoom a bit?
So I don't know. It's okay.
Yeah, very good. So where there is a little blue circle, this is where I apply the move, I don't know how to call it, when we apply the Conway relation.
Right. So you are using relation here, right?
Yes,
In
where
this
there
point.
is some, yes, exactly. So on the, if we make this crossing put on the top, it will give us the trivial one. And if we smooth the crossing, it will give us the one on the right. But it's clear?
I don't think so. So I'm looking. Yes, this is absolutely correct. This is absolutely correct. But here this is your orientation, right?
Yes.
Go here and then here, this way, and then you are going here, right? So what I'm not sure. This one, I don't think so that here is correct. So look, you take this one, then you going this way, and this way, and this way, right?
Yeah.
This is link.
Yes, the link. Yes.
This is two-component link, and a little bit tricky because you have, by the way, you can look, link with 1, 2, 3 crossings, right? Am I right?
1, 2, 3, 4.
Yes, so you have maybe it's white heat link or something. It is you have so we can calculate, for example, the linking number. Let us calculate the linking number. So the linking number here is -1. Here is okay. I'm just looking. We are going this way. So here, this is -1. Here, -1. Here, again, -1, -1. So we have link with the linking number -2, right?
Mm-hmm.
So link where they linked 2 times. So it is not like here. It is more complicated formula for Alexander, and will be so. This is not correct. Let us yeah. So it will be this link. I calculated, but I'm not sure that I can reproduce this with the mouse. Excuse me. Look. Mm-hmm. Excuse me, I need to find my calculations. Okay. Maybe somebody else, we can ask other people. No, so there should be more complicated formula. Okay, anyway, let us consider the next one. So the next one. Yes, I think this is more or less correct. Yes, so let us consider this one. Yes, so you are making, so cinquefoil, this is beautiful star. right? And you are making resolution here, right?
Yes, where the little cycle is.
Let me zoom it. Right. So you make it here. Then you are getting, what is this? This is like trefoil, something, right?
No, I just maybe it's a trefoil.
Because you can use Reidemeister through here.
Yeah, indeed.
Get something
Yeah.
with two crossings, and you can use trefoil, right?
Yeah.
The same way here. The same way here. And you can get, but this is, I think, will be more complicated. You should make probably again, you get a link, no? You are not distinguishing them, right?
No, I'm not.
Excuse me, I'm not correct. So let us consider, what do you have? You have here this direction and this direction, right? So you should make this smoothing.
Here, the right one is always the smoothing.
Yes. So you have this smoothing going this way. So what does it mean you have here crossing? I don't understand.
No. Here where the mouse is, I just forgot to erase the arrows. There is no crossing.
So right, okay. So let us consider what it is. Going this way, this way, this way, this way at first, this way, and this. So
Yes,
this will be
this
will be one component, and
yes.
then if we go this way, then this way, this way, this way, this way. So it will be two components, right?
Yes.
So we see that how many we get? 1, 2, 3, 4, right? So again, we have this way, this way, this way, this way. So right here, this way, right? And this way, this way, this way. So we have two-component link, right? Two-component link with crossing. So let us consider this way and this way. Here we have class 1. Here we, sorry. So here we have this way and this way. So -1, this direction. -1. So here and here, again -1, then here and here -1. So again we have this two-component link with linking number -2, right? Then we have to resolve them. Yes, I think this may be correct. Okay, Very good. So yeah, and this is the linking number. Here you have just hops link, right?
Yes.
So this is why we have two components. This is 0.
No, by the smoothing, we get just the trivial node, and on the left we get two components.
Right. And here we have Z4, right? So if we have this stuff, we can resolve here.
Z3. We should get Z3.
Right.
I think.
Okay. What's next?
I think that.
Sorry, the Borromean. Did you calculate the Borromean?
Oh,
No?
I think I forgot that. I think I forgot to do it. I think I forgot.
Okay, so Borromean you didn't calculate, right?
No, I think I forgot to do it.
So this is what I see. This is what I see in your.
Yeah, no, it is not. No, I just forgot to do it, most probably.
Okay, no problem. So we spent a lot of time in this. So let us start the next lecture. So about grades. So this is I don't know what's happening. Do you see the lecture?
Yes.
We start with braids now. Braids are more regular object than that of knots, but they are used to study knots, for example, but they are interesting by themselves. So what do we do? Let us consider our points, finite number. You have the same B1, B2, so on, and you have curves which join the endpoints here, endpoints here. So A1 may go to another one, and so on. The only condition is that the situation is monotonic, so you are not so if you made a section by any plane.
There is a problem because we don't hear you a few seconds and then the sound come back. The image and sound just freeze for some time.
Sorry, what is the problem? Yeah, I also have problems that sometimes disappeared. I don't know why it is happening. Because this is the version from the higher school, it is paid, so it's not, in principle, it is not to be interrupted.
No, but I think there is some internet problem or something because sometimes just the sound freezes and the screen as well.
Do you see the screen, Rafael?
Yes, I do.
Very good. So this is trivial picture. See, this is the monotonicity. And yes, this is another stuff. If you have the AI, consider the corresponding number, this will be the permutation. If you have permutation of n numbers or letters in the lower, it means that there is a map to okay. This is how the composition law is defined. So you have one. Traditionally in braids, it is depicted from the upper strand to the lower strand, but you can also do anywhere, horizontally or vice versa, going up. But traditionally, this is because of the human braids. It is human braids you are making and you're constructing from the high to the lower level. So here you have one braid, here you have another braid, you just join them, forget about intermediate plane, and if you are formal, if you fix that the height should be, for example, equal to 1, then you press and make the corresponding that the result is also the same height as before, right? So, of course, this gives a law of composition in this geometric braid. So now you may consider all these things up to isotopy, and up to isotopy. So now the braid is not this picture with curves. It is called geometrical braids. So but you should, as we are everything considering up to isotopy, you can, of course, move this picture, but you should move this picture in the class of braids. So you are not allowed to do again this up and down this picture of the sine function. So isotopy in the class of braids is possible. Then braid is what we call geometrical braid and its class of equivalence. This is the braid. And because of this, we can have a map. This is what we call the braid up to isotopy. Then there is a map, actually evident that this map is an epimorphism, and there is a kernel of this map, and the kernel is called pure braid group. So you may consider this stuff, everything is not completely strict. To make the previous consideration strict, we consider the notion of configuration space. So let us consider the following. So if we look at the first picture and you consider the endpoints on the plane. Let it be here. Let it be here just plane R2, and you consider endpoints on the plane. So, and then this can be formalized by the notion of configuration space. The notion of configuration space. So the points actually, when we are considering the projection, essential that the points should be different. This is the idea of configuration space. So I make the formal definition as follows, that you consider the Cartesian product of R2 in M case, if you want to consider M points, like here, and you take the points which are different. This means that the points are different, that the points with index I does not coincide with the points of index J, if of course I is not equal to J. So this is the space, what we can say the regular points. It means that when you make permutation of these points, you always have in your orbit, you always have the same cardinality of this. So this what is sometimes called the configuration space of M different points in R2. But now you can make the action. So actually, what do you mean? You simply make a permutation of these points. They are all different, so every time you will get different points. So you have an orbit, and if you factorize by this orbit, you have what is really can be considered as a configuration space. Because what does it mean, the word configuration? Sorry for that. It means that you don't consider which one is the first one, which one is the second one, because you are already made action of permutation group. So configuration space after action is the following, that you consider the plane, say this is a plane, and here is the, I'm sorry, and here is the points. If you are considering just the case that they are different, if you are considering R2 in the power of M, then you see that which one is the first, because if you considering this one, this is the set of ordered M tuples. But when you, so if you now make this diagonal, the points which are sometimes equal, and then you make the action of symmetric group, then what is called configuration. So here you don't see which point is the first one, which point is the second one. You just consider this object as a configuration. This is because it is called the configuration space. So, Rafael, other question at the moment?
No, so far it's okay.
Very good. Then we shall go. And now you can define the braid group on M strands, the fundamental group of configuration space. And here, now, in this definition, you have for free that this is a group, because this is fundamental group of configuration space. And if you now consider ordered configuration space, this is just the R2 to the power n minus diagonal, then you have a map. From here to here. And now, if you consider the short exact sequence of this map, which is a covering space, you have this thing. You have, you have this one. So this is the braids, the fundamental group of configuration space. That means that after action, then you have a projection of sigma arm. This is sigma, sorry, I made a problem with indices. This should be M. And here you have unordered configuration space. So because this group acts, so the fiber is exactly equal by this. So you can just, if this is a projection, then at each point fiber is sigma m. And that's why when you are considering, if you have this is covering space, this is the fiber, then of course you have pi 1 of this covering space, this is here, pi 1 of this space, this is here, and then you have of course the group which acts. So this is the short exact sequence of the of this covering space. Okay, of this covering, better to say. So okay, then let's use this and go further. So let us consider the following braids. Here I made this is positive. So it depends when, in what time you are making what positive, what negative. So this means that now this one I consider as positive because I can explain. Because direction which comes from everyday life braid is here. And this is actually negative, right? This is negative crossing what we already. So usually as for me it's more convenient. I don't know why I use this as positive, but anyway, let it be positive. Okay, so this is the braid, which is called standardly it is called sigma I. Sorry, sigma I. The braid goes from number I to number I plus 1, right? This is no. Sorry, I made a mistake. Okay, so this is sigma 1. this is, I only wanted to make note that this is sigma I. Okay. Then, of course, if you change crossing here, you will have sigma I minus 1, right? You'll have sigma 1 minus 1, and you'll see that they are, one is, the composition is equal to the identical braid, right? So actually their history of the braids starts with the following work of Artin, who gave a presentation for braid groups, and who gave a presentation. This is the following presentation. The fact that this is a presentation is evident because here it means that when they are too far, they commute. This is evident. And this is nothing but the third Reidemeister move. So it's evident that this is the relation should be satisfied. The fact that these guys are gives you they generate the same as Raphael. You were looking that the matrix generate. It's more simple than if you just consider arbitrary braid. Suppose that you have arbitrary braid, then you should move. You have many crossings in this box, and suppose now that you move a little bit your braid which is here in this box, in such a way that at each level there should be only one crossing. Each level, you always can do this because in your braid it is only finite number of crossings. So you can move in such a way that there are, at each level, there is only one crossing. All other strands are just like here, right? And if you now read this word, for example, from here to here, you see that at each level you have only one crossing. This means that each braid can be written as the word of either sigma I or sigma I minus 1. So this means that, but if you have groups, you usually don't write that your group is generated by sigma I and sigma I minus 1. This is by default that your group is given like here. The same way, but a little bit more difficult, you can understand that if you consider all the relations, in the word of all relations, you can divide your relations in either these relations, either these relations. So the general positions of relations are also read as the composition of primitive one. Primitive are the following relations. This is maybe not a proof, but explanations for why there should be these relations. So this, anyway, this is a classic Artin presentation of this. Something more about some some geometric properties. This is nothing but you can join, you can put your braid on n strands in the braid on n+1 strand. So if you have, this is very geometrical stuff, that suppose you have braid on n strands, you simply add a vertical line, this one, then you'll have now you will have n+1 strand. So this is an evident map, and of course, if you have connections here, you have connections here. So evidently, this is a homomorphism of groups. So actually, this is connected with the fact that here you have projection to the symmetric group on n letters, here symmetric group of n+1, and the square should be commuted. So if you look now at the presentation, the canonical presentation of symmetric group, you have the following. Of course, the two involutions, they commute if they are not close enough. Then there is some kind of Reidemeister move number 3, and then of course if you have involution i+1, then squared i+1, it will be the it will squared, it will be 1, and evidently we have this homomorphism because sigma 1, and this is actually the braid relations. You simply add one more relation to get symmetric. So this is another way. There is another way to introduce braids. The first one was the braids in 3 space. Another is fundamental group. This is the third one. This is like Reidemeister introduced knot theory, like from knot diagrams. Now you can consider something as braid diagrams. Braid diagram is something which is depicted on the plane, and you will have the same as you have the Reidemeister moves for the knots. You should have Reidemeister moves for braid diagram. So you can construct your braid theory starting with braid diagrams. You can define the multiplication of braid diagrams, and you'll see that Reidemeister moves is okay with respect to multiplication. So you will have an object which will be the group. Class of equivalence of braid diagrams with respect to the Reidemeister move. So Raphael, do you hear me?
Yes, I do.
So please tell me why we need not to consider Reidemeister 1.
Well, there is no braid that comes back to the top.
Yes, exactly. Because Reidemeister 1 is, in Reidemeister 1, you have not monotonic curves. So you should consider only Reidemeister 2 and Reidemeister 3, right? Very good. Thank you. So, okay, so I'm sorry, Raphael. How do you think maybe we'll have break for 5-10 minutes? I'll
Yeah, no problem. Sure.
Cup of tea. So just
sure.
5 to 10 minutes.
Okay.
Are you with me?
Yes.
Very good. So braid group has also interesting interpretation from the point of view of pure algebra. Let Fn be a free group of rank n. It means that the free group on n generators, right? Let us consider the group of automorphism. It means that you take Fn to Fn, and this is the isomorphisms, epimorphism and injections. So all these things you can multiply them by composition. This gives you the automorphism group. You can construct, of course, automorphism group for any group. Now we are considering Fn with n generators, right? And let us do the following thing. That let us consider, because it is free, you don't bother about relations. If you put your generators somewhere, it will be okay. Your homomorphism will be constructed. So what are you doing? You consider the following map. xi went to xi plus 1. xi plus 1 in its turn goes a little bit complicated word. I plus 1 minus 1, xi plus 1. So conjugation of I with the help of I plus 1. So if we consider the following things for abelian groups, then this will be permutation. Permutation and even involution. I goes to I plus 1 will go to I, because this commutes and this will disappear. But in a non-commutative case, it's essential that our image of xi plus 1 is the following. And what, as far as concerned other things, it is the following, that they are constant. So xj goes to xj if j is not I plus 1. So only a small portion of the generators is concerned. So the fact that this is a homomorphism, but in fact, one can prove, we don't have time, that this will be automorphism. For example, you see that actually you can, and maybe I give this as an exercise to construct inverse one. So this is automorphism. And the Artin theorem is the following. Now, let us construct the following map. The theorem 1 is that this formula defines correctly a homomorphism. So from sigma I, you associate this automorphism defined by these maps. So maybe I need to tell that if you have a braid group, it is sufficient only to map the generators. The homomorphism will be defined automatically. Okay? So Artin theorem is the following. that the formula defines correctly a homomorphism. And this homomorphism is an inclusion actually. So a group can be considered as an automorphism group of the free group. And why this theorem is interesting for us? Of course, it's interesting because it gives us the relation between purely algebraic object, as you can consider, and purely geometric, maybe not purely, but geometric object. But also because it gives the solution of the word problem for the braid group. So I can explain this in the following form. Maybe it will be almost the proof. So this fact, the monomorphism, gives you the solution of the word problem in braid. Suppose, what does it mean, word problem in braid? Suppose you have a word in sigma. Suppose that you have a word in generators, word in sigmas, right? In sigma I. So it may be sigma I1, epsilon 1, and so on, epsilon sigma I k, epsilon k. This is just a word, right? You consider now the list of generators. X1, Xn. Because each word, it is an element of automorphism. Is an element of automorphism. So it acts on this set of generators. Each word sends these to another word, maybe V of X. And this is, so V1, Vn, right? And you have another word, so say W2. It is also a word in sigmas. Now you consider the action of sigma 1, this will be this one. You consider now the action of W2. This will be another set of words. But here in Fn, you have a solution of word problem. Each word Vi you can reduce to the reduced form. And you now simply can consider two lists. You have one list and you have another list. Say this will be V1, this will be, say, V2, 1, and so on. V2, N. You just compare, imagine that you are a computer, you just formally consider these words in reduced form. And the automorphism coincides if these reduced words, all of them should be the same. This is a complete solution of the word problem for braid group. And it is actually based on two things. Solution of the word problem in solution in the word problem in free group, and Artin theorem about injection of the braid group in the automorphism group of the free group. Other questions?
No, it's okay.
So actually, you see why I in detail explain the solution of the word problem for free group, not because it's simple by itself, but because we concretely use this in solution of the word problem for break group. Okay, so let us continue. Let us continue. Another thing is also interesting in the following form, that it may give another phase of the break group. Another phase of the break group, which is connected with what is called the mapping class group. So, sorry, excuse me, please. So let us consider now a disk. Let us consider now a disk with endpoints deleted. Disk with endpoints deleted. So you know that the fundamental group of the disk with endpoint deleted is exactly our free group. So in this picture you see that, don't look at here, only here. You have you fix the initial point of your fundamental group somewhere in the boundary of a disk on a circle, and this is the loop which gives you the generator of the free group, fundamental group. This is another generator. And now simply make the rotation. So these are two neighboring points. You put a small circle here and make a rotation. So here in the negative direction, I don't know why I put negative one. In some direction, clockwise. And in such a way that only these 2 points are involved. You have rotation here on pi, 180 degrees, and then your rotation becomes smaller and smaller, and at the boundary of this small disk, which is included in the big disk, it is zero. Excuse me. I look for the. I get an email message from one participant. So if you make this map, what will happen? If you have this rotation, then this loop goes simply to this loop. I didn't make picture because it will make the whole picture even more difficult. So this loop, the left loop, takes place the right loop, somewhere here. But what will happen with the right loop? There should be a loop now, because point xi plus 1 went to the point xi. So it should be a loop which goes around xi. And if you now concretely construct the image of this loop, the right one, after this map, after this pi rotation, you see that it goes somewhere here. Like this one, at first it goes around. It is not a loop around anymore I plus 1, but a loop around xi. And if you read this loop, this is a loop in a disk, function disk, so it should be read as a word of xi minus 1. So this is the following form. What does it mean? the whole thing. The whole thing means that braid group you can consider as the mapping class group, so the group up to isotopy of punctured disks. So consider, I didn't write this because it will take much more time than we have. So now consider what is the mapping class group. Consider the punctured disk. Consider now punctured disk. So let it be disk with n punctured, and you consider homeomorphism of this disk to itself, and consider all the homeomorphism, and then up to isotopy. You have a mapping class group. Sorry, I forgot to tell that the circle, the boundary of this disk, should be fixed point by point. So you consider all this homeomorphism up to isotopy. And this will be exactly, following this consideration, this will be exactly the braid group. Exactly the braid group. The braid group has, and the previous form of the automorphism of free group is the algebraic side of this topological form of the isotopy of punctured disks. So if you now consider that punctures should be preserved not as a set, as here, for example, the punctures are supposed to change their places, then you see that it will be, you'll get the mapping class group of punctured disks with punctured fixed point by point. So this is the difference between the previous case. In the previous case, as the braid group itself, the big braid group, this is the mapping class group of a punctured disk, and the set of punctured is fixed as a set. And here are the generators. So this small twist, P by P, this is the generator sigma I. And here is a mapping class group of punctured disks, where points punctured are preserved point by point. This will be the pure braid group. This will be the pure braid group. Other question at the moment?
All is okay.
Very good. Then, now let us start to consider the pure braid group. Let us start to consider pure braid group. EN is written here. And I made the following picture. So for simplicity, this is going the first one. So let us consider a braid such that it starts with number J, and goes around here number 1, but in principle it goes around number I. So let it be number I. This is number I. And here there are other, and here is 1. Right? So it goes from J to I, goes around and returns this way. So it doesn't touch other than other strands, only the strand number I. Sure that I should be less than J. Okay? We denote it by denoted by A. Here is A1J, but in general this is AIJ. So then these elements satisfy some relations which were obtained by Werner Burau in 30s. So I forgot to tell that Artin's work on his theorem presentation is the work of 1925, and in about 1935, this is the work of Werner Burau about the presentation for the pure braid group. So about something about relations. So unfortunately, relations are not so regular. For example, if you want to involve these elements, then there should be negative degrees, right? And relations are the following. It's quite not evident to comment all the relations, but relations, the first one is quite simple to comment. For example, what does it mean that they commute? It means, for example, that if you have here, it would be AIJ, and now you have another one, AKL, which goes this way. Sorry, it's no. Okay. Right. So let it be this KM or whatever. I noticed that you can move this up, this down, and if they are far enough, then it's okay. Then they commute. But also you may construct the same, for example, one inside the other. So for example, this one goes here, goes around, and again here. So you see that one inside other, inside in the sense that A and J are much bigger than this K and L. Then you see also they can move one inside other, no problem. So this is the relations which involve the generators, the Burau generators here. Okay. Other much more difficult to interpret, but there is a theorem, 1935 probably, Werner-Burau, that this gives the complete list of relations for the pure braid group. And now I just want to mention the Markov theorem on the following stuff, that actually how every element of the braid group can be uniquely written in this normal form. It appeared in 35 in the work of Markov in Russian, so it's not known actually in the West as the Markov form, because it was in Russian, and in 47 Artin published a second work on braid group, where he named this probabilistic process the combing of braids. So, but anyway, this is the Markov normal form, and so this is in some sense another way of get a solution of the word problem for the braid group. I don't have time to go in details. I only want to make that Markov constructed the series of subgroups. So suppose that this is the complete pure braid group, and this is group generated only by the elements of Aij with j greater than some element k, so only part of them. Then Markov proved that the quotient is a free group. So it's very interesting, and actually the like a foundation stone of the for the pure braid group, that it is constructed in such a way that it is built by free group. So you start with one, then you factor by the second, and then you get a free group on these generators. So, for example, let us consider the following stuff: that you fix n, and you take subgroup the n factor n minus 1. What does it mean? All these elements, Aij with j less than n, they are killed. So it means that you can only consider the elements A, I, n. The second index, you have only this one. And so it is evident that you get, in this case, the free group, which is generated by the loops, which goes like here, and this is Aij goes like here, goes around each, and this will be the free group. So this, in this case, this is the free group. So this is what I'm depicted. This is the Artin's theorem. Sorry, this is the P K minus 1, Pn minus 1, Pn. You have A, I, N. They will be the generators. Then you build and the number of generation becomes smaller and smaller. And finally you have F1. Okay. So this is Markov normal form, which gives a solution. Okay, so maybe I skip this, and I would like to now, as we are speaking about Markov, so I would like to give another, and this is very well known because this work of Markov, I think 35, it was published in German. So you see that at that time the papers on this stuff which we are considering were basically published in German. The work of Artin was published in German. It is in the notes on the seminar of Hamburg, Burau in the same journal, and of course, Reidemeister book was in German and so on. So the work of Artin, so Markov, and at first the simple theorem of Alexander, I didn't wrote it down, but it is very simple theorem that I don't have time to look in details on it, but it is the following, that let us consider the following procedure of the closure of braids. So in this cube you have a braid. In the cube you have a braid. So this is a braid, right? This is a cube. And now you make a closure of braid somewhere outside of this cube. You join the point 1 in the upper plane to the point 1 with lower plane. The same way, the point A2, the point 2 with the point 2, the point N with point N. Somewhere that these lines, they are not linked. This is just circles. In order to be sure, you can use this picture that they are going exactly at the surface of the cube, and you are sure that they are not linked. Okay. So what do you have if you do this? Rafael, what do you have?
Sorry again?
You have a braid on N strands. You applied the procedure of closure, this procedure, geometrically depicted here. The procedure of closure for braid. So what do you have? What object do you have now?
Wait again, what is the procedure of closure? I got distracted.
So you join somewhere here in the cube, you have braid.
Yeah.
But outside...
knot. The knot, no?
Yes.
Yeah, no.
Yes, we can. So we get link. Generally speaking, we get link.
Link, yeah.
And there is a theorem, Alexander theorem, that you can get any knot. Any knot you can obtain. This is not difficult theorem. There are now many algorithms how to do this. So any knot you can obtain as a closure of some braid. So from braids to knot, this procedure gives you an epimorphism. Very good. But if you have epimorphism, then you can ask for the kernel in general sense. Of course, it is not groups, not linear, but just to say which two braids are mapped to the same knot. This is very interesting because in this case, if you consider equivalence classes, then this will be exactly all the links. The equivalence classes of braids will be links because Alexander theorem gives you an epimorphism. And the answer on this question was given by Markov. Answer was given by Markov. So suppose two following, oh yeah, I made this, finally I wrote down that any link can be represented of closed braids. So this is the Alexander theorem, I wrote it down. So suppose now two following Markov moves. So you have a braid and you consider the conjugate of it. Just in algebraic sense, you consider the conjugate. Then it's a little bit more complicated. This map, which we're considering from braids on n strands to braids on n+1 strands, and then multiplicating by sigma n. So this is another Markov moves. So let us consider Markov moves from geometrical point of view. What does they mean? Okay, so sorry. No, I'm stupid. So, yes. So you have a braid. Maybe I denoted betas, right? And you have multiplications of braids. This is gamma. This is gamma -1. This is the first Markov move. You have beta, you have gamma, beta, gamma -1. Now, this is a braid. You constructed the closure. Now you construct a closure for this one. What do you see? Now the closure, it means that there are n strands. I don't have time to depict all n strands. But this is the closure. This is the closure. This is a knot. This is a knot. Link. So now you start to move gamma here and gamma 1 here. Because now it is possible. You have this junction. So what do you have? Here is gamma. Here is gamma -1. maybe you need to. Okay. So, but they kill one another, and you will have simply an unknotted strands. So gamma and gamma 1 kill themselves. You see that you have the same link. You started with beta, or you start with gamma, beta, gamma minus 1. You have the same for any gamma. Is it okay, Rafael?
Yes, it's okay.
Very good. So if it's okay, then let us consider the second Markov move. What will happen? You have beta, and then I try to make picture. You have beta. You map this beta to n plus 1. Here you have a strand. And then you multiply by sigma n. This is sigma n, the last one. Or sigma n minus 1. No problem. And then you have maybe here you have this one, and you have this one, right? So what do you see? What do you see with beta? The closure of beta and closure of beta, j of beta multiplied by sigma n. What do you see here, Rafael? This is Reidemeister 1.
The move, the one, yeah. Ah, yes.
Reidemeister 1. Our forgotten Reidemeister 1, which was not applicable to braids. But when we go to knots, you should apply it. And that's why you have the same. So these are the same. The same. The closure of beta and closure of beta times sigma n. This is the second Markov move. So of course, it is evident from geometrical point of view how to verify that Markov moves, they give the same result for closure, right? But the great Markov theorem is the following, that in some sense inverse is also true. That now suppose that you have two braids, B and B prime, not necessarily the same number of strands. Then suppose that beta and beta prime represent the same link. They represent the same link. And then beta and beta prime can be connected with the following chain of Markov moves. So Markov moves or their inverses. So if you want to consider only Markov moves, you should place arrow in opposite direction. But I consider in the following way. So it is, you start with beta, let it be renamed beta 0. Then you have this arrow. This is either Markov move or its inverse. Of course, inverse of the first Markov move is itself. Actually, the inverse you need when you are mentioning the second Markov moves. So you mean that beta is equivalent to d beta sigma n. Inverse is that the braid with n+1 strands is equivalent to a braid with n strands. So it's possible that here each arrow either makes bigger, so number of strands here may be n+1. Here, if you apply direct Markov move, or it may be n-1 if you have the opposite of the second Markov move. If you apply the first Markov move, the conjugation, then you'll have the same. So here is, and this is actually the main problem. The main problem in the application of Markov theorem is that in the Markov process, the number of strands may change. For example, you start with some braid, then you can go far, far away with the number of strands very big. Then you get here conjugation. And then again, you are diminishing the number of strands. Even the braid of the same number of strands, say here, they may be Markov equivalent using conjugation very, very far. This is the main problem, that this is not bounded. They may be equivalent somewhere very far. So Markov theorem has, of course, a big meaning, but in some sense theoretical meaning. So it's quite difficult to apply it directly. So this is our Markov theorem. Okay. So other questions at the moment? Other questions, remarks?
No, it looks okay.
Very good. Very good. Very good. So we can now formalize this in the following form. Sorry. Take now the disjoint union of all braid groups, because they are connected. So you have a copy of B1. This is B1 is trivial. You have just a group of one element. B2 you have Z. B3 you have the group of trefoil and so on. And at that moment they are all disconnected. You just make a disjoint union of all of them. This I denoted this way. And then by these chains you introduce the equivalence relation. So by the chains, as usual in the general nonsense of the equivalence relations, it means that the equivalence relations generated by moves 1 and 2 and their inverses. It is given by the classes. This is given by the chain, right? So, and they generate the equivalence relation. So it is evident that if beta and beta prime are connected with this chain, then you can construct, say you have, say you have beta second here, and again you have chains. You have a chain of moves. Then, of course, you have a chain from beta to beta prime. And of course, beta is equivalent to itself by the empty chain. So this is chains you give the real equivalence relation. We constructed in this object, we constructed equivalence relation, and this is the set of equivalence classes in the joint union of all braids. And the Markov theorem, reformulation of the Markov theorem, says that this is equivalent to isotopy types of say isotopy types of links. All right. So the formulation of the Markov theorem is that all links that we are studying several months now are equivalent to the following form. This is the set of equivalent classes of braids. Okay. So, other questions for maybe all the questions for today? Rafael?
No, I'm okay.
Tatiana, maybe you have a question?
Нет, вопросов нет.
I'm very happy that you are with us. Sorry for last time that you cannot join us. Okay. Nikita, are you with us?
Yeah, I'm here. Sorry. Hello.
Hello.
Hello,
You
I'm
have
here.
a question?
No.
Professor Markarian?
Yes, no. Thank you.
I'm very happy. I'm very happy with you.
Me too.
Okay. So then this is okay for today. Thank you very much. So The next lecture will be in a week. Maybe it will be the last one. So I invite you all. Thank you very much for your presence. Goodbye.
Bye-bye.
Thank you. Goodbye.